Okay, let's unpack this deep dive you've brought us today. We're tackling a challenge that sits really at the heart of building more capable AI. How do we get these large language models, these, incredible systems built on predicting the next word? How
Yeah.
do we get them to handle tasks that demand absolute precision, like certainty, things like mathematics?
Right. Yeah, exactly. I mean, they're amazing at generating fluent text. It sounds intelligent, right?
Yeah.
But getting them to be reliably correct, especially when computation is involved, that's a whole different ballgame.
Right, it's the core nature, isn't it? They're trained on just vast amounts of text data. They learn patterns, relationships, probabilities of words coming next.
Which makes them fantastic for, understanding context, generating creative stuff, summarizing, carrying on conversations, all that language-based work.
But math isn't probabilistic, it's
Mhm.
deterministic.
Totally. 2 plus 2 has to be 4, always. You've got these complex equations. They have one right answer derived from a strict set of rules, operations.
Mhm.
You can't just like probabilistically guess your way to the right answer consistently.
So relying on that text generation skill for complex math seems, well, inherently difficult.
It is. It's like asking, I don't know, asking a poet to be an accountant.
Huh. Yeah. Okay. They might write a beautiful poem about accounting.
But they can't necessarily balance your books accurately. That's a good way to put it. So for anything beyond maybe recalling simple facts or like basic arithmetic that just happened to be in the training data, LLMs really struggle. That step-by-step rigorous computation, that's the tough part.
And that limitation,
Yep.
it points directly to needing something.
External. Right.
Exactly. For tasks needing precise calculation, verifiable logic, you often need a tool. You need a dedicated environment where you can do those deterministic computations. Could be a calculator, a symbolic solver, or, in the context of the research we're looking at today, a code interpreter. And the really fascinating question this work explores isn't just how to, tell an LLM, hey, use this calculator, but how it can actually learn to decide, on its own, spontaneously, that using a tool is the right move for solving a particular problem.
That's the crux of it. We're diving into research centered around something they call ZeroTIR. Stands for Zero Shot Tool Integrated Reasoning.
Zero-shot tool integrated reasoning.
And the core idea here is using reinforcement learning RL to train a base LLM. The goal is for it to spontaneously learn when and how to call up and use an external tool like a code interpreter. Not because we told it to, but because it discovers that doing so actually helps it succeed at the task. It learns that tool use gets it the reward.
Okay, so the sources we're digging into for this. We've got the main research paper on this Zero-TIR using RL. And you mentioned there's a specific math problem they use as an example.
Yep, a math problem that really highlights the difference between trying to solve it with pure reasoning versus using code.
Yeah.
And then we have the data figures tables that show the results, how this learning actually happens over time, the dynamics of it all.
Got it. So our mission for this deep dive then, what are we focusing on?
We really want to cut through the noise and pull out the key insights. We're going to focus squarely on the technical mechanisms behind ZeroTIR. How does this RL approach actually teach the model to use tools? And what are the implications of what the researchers found? Especially these patterns they observe. They call them agent RL scaling laws.
Agent RL scaling laws. Okay, we'll definitely need to unpack that.
We want to understand the mechanics of how this autonomous skill gets acquired and the empirical patterns that seem to govern it. And just to be clear for everyone listening, we're deliberately setting aside the broader ethical or societal questions for this specific exploration. Our focus today is purely on the technology itself, the methods, the results, and what it means for building more capable, more reliable AI agents.
Right. Keeping it focused on the tech. And why should this matter to you, the listener? Well, because getting AI to reliably perform complex, verifiable computations, that's fundamental for tons of real-world applications. Think scientific research, data analysis, engineering.
Absolutely. And understanding how an AI can learn this crucial skill, especially without being explicitly handheld and told when to use a tool, that's a really significant piece of the puzzle for developing the next generation of AI capabilities. It's about building agents that can actually figure things out more effectively.
So let's dive in. We should probably start by really hammering home that core challenge you mentioned. LLMs and math. Why is it so hard for them?
Right. We touched on it, but let's solidify it. LLMs at their core are designed for processing and generating human language. They operate by predicting the next token, the next word, or part of a word based on these massive statistical patterns they've learned from, basically the entire internet's worth of text.
So they generate sequences of words that are probable, that sound coherent given the context.
Exactly.
Yeah.
But math problems, they require a totally different kind of process. Logical deduction, precise calculations, following strict rules. It's not about generating a likely sequence of numbers and symbols. It's about performing exact operations.
So the LLM might generate text that describes how to solve a math problem, and it might even look convincing.
But the actual numerical result derived purely within that text generation. It's highly susceptible to error. It's still operating probabilistically, not deterministically. It might get simple stuff right if it saw it enough times in training, but step-by-step calculation, that's where it often falls down.
So anything requiring more than just remembering an answer or doing a super basic arithmetic step, pure text generation just isn't reliable enough.
Pretty much, which is why for complex or multi-step math, you fundamentally need that external deterministic environment. You need something that can perform the calculations and verify the results with certainty.
And the sources, you said, have a perfect example of this, that permutation problem.
Oh yeah, it's a great one. Vividly illustrates the difference.
Remind us what it was again. Finding the number of 8-digit integers.
Right. Using each digit from 1 to 8 exactly once,
Yeah.
and the number has to be divisible by 22. Then find the difference between that number and 2025.
Okay, so definitely not trivial. Requires some real work.
For sure. You need the divisibility rules for 2 and 11, since 22 is 2 times 11. And you need to combine that with combinatorial logic, maybe iterating through permutations or carefully counting based on those constraints. It's involved.
And the sources show how a pure LLM reasoning approach tackles this. What happens?
Well, the example in the source is it's classic LLM behavior. It correctly identifies the rules. It knows the number must end in an even digit, 2, 4, 6, or 8, for divisibility by 2. It knows the alternating sum of digits must be a multiple of 11 for divisibility by 11. So far, so good. Then it tries to reason combinatorially about how many permutations meet these rules. And this is where it gets shaky. It describes a process, uses mathematical language, but the actual application of that logic within the text generation, it's flawed. The final calculation it comes up with is 27,648 such integers.
27,648, which is wrong.
Yeah, way off. The correct number is much lower. Now, contrast that with the second solution shown in the source as the one that uses code.
How does that one approach it? It doesn't try to do the combinatorics itself.
Exactly. It recognizes implicitly that it needs a precise, verifiable count. So it generates Python code.
Ah, okay. It offloads the work.
Precisely. The code it generates is straightforward. It iterates through all possible permutations of the digits 1 through 8.
How many is that? A lot.
It's 8 factorial, which is 40,320. So not a trivial number to check manually.
Definitely not.
So the code generates each permutation, forms the 8-digit number. Then, using Python's built-in modulo operator, the %, it just checks. Is this number perfectly divisible by 22?
Simple check. Does the remainder equal 0?
Exactly. A definitive yes or no. The code runs this check for all 40,320 permutations. It counts up the ones that pass the divisibility test, and then it performs the final subtraction from 2025.
And the result from the code execution?
The output shown in the source is 2304,279, meaning the correct number of integers is 2304. And the difference from 2025 is 279.
Wow. Okay, 27,648 from pure reasoning versus 2304 from code execution. That's not even close.
It's a huge difference, and it makes the point so powerfully. The LLM could articulate the rules. It could even attempt the logical steps, but it failed at the precise application, the computation, the model that used the code interpreter. It got it exactly right because it handed off the deterministic, verifiable work to a tool built for that job.
It really highlights the gap, doesn't it? LLMs are great at generating text that looks like a solution, but for that guaranteed correctness, especially in math, they need the ability to call on these external, precise tools.
That's the core issue this research is tackling.
So if the problem is that clear, what were the standard ways people tried to give LLMs these tool-using abilities before this ZeroTIR approach came along?
Well, broadly speaking, you can lump past methods into a couple of main categories. The first one is supervised fine-tuning, or SFT.
Okay, SFT. That involves showing the model lots of examples, right?
Exactly. You create a data set where, for each math problem, the training data includes not just the problem, but a full step-by-step solution that explicitly shows the tool being used. So it would include the part where the model should have outputted, say, Python, the specific code it should write, the expected output from running that code, and then maybe any subsequent reasoning steps.
So you're basically teaching it to imitate a perfect tool-using process.
Precisely. You're showing it, this is the trajectory, this is how you use the tool at this point. And this can work, definitely. but it needs really expensive, high-quality data sets showing how to use the tool for a whole bunch of different problems.
And the downside.
The sources point out a couple. One is overfitting. The model might get really good at reproducing the specific tool use patterns it saw in training, but then struggle to adapt or figure out how to use the tool for slightly different problems it hasn't seen before.
So it's learning to mimic the examples, not necessarily to understand the underlying need for the tool.
Yeah, that's a good way to think about it. It's learning imitation, not necessarily strategic decision-making about when and why using the tool is the best approach.
Okay, so SFT is one way. What's the other main approach?
The other is often called prompt-based tool-integrated reasoning, or prompted TIR. This is less about training the model on specific step-by-step examples and more about designing the system or the prompt itself to trigger the tool use.
How does that work? Like you tell it in the prompt to use code.
Yeah, that's one way. You might explicitly structure your prompt to say something like, to solve this problem, please output any necessary Python code within Python blocks. Or the system surrounding the model might be designed to watch the output, and if it sees a specific trigger, like the model outputting Python, it automatically intercepts that, sends the code to an interpreter, gets the result, and feeds it back.
Ah, okay. So in this case, the model isn't really autonomously deciding to use the tool based on like the difficulty of the problem or its own internal state. It's more like it's reacting to a rule or a cue that's been embedded either in the prompt or in the system wrapper around it.
Exactly. It's responding to an external trigger or instruction. And this is effective. Models like Quinn 2.5 Math Instruct mentioned in the sources use this kind of approach successfully. But the key limitation, the philosophical difference perhaps, is that the decision to use the tool isn't emerging from the model's own understanding that the task requires it for success. It's being externally dictated or prompted.
And this is where ZeroTIR comes in, offering a different path. The sources mention that ZeroTIR applying reinforcement learning directly to base models, using only outcome-based rewards, has shown some really exciting results before in getting models to like self-correct and improve without needing all that detailed step-by-step data.
Yes, ZeroTIR has definitely shown promise for developing these kinds of emergent abilities. And the critical difference from SFT is that reward structure. With outcome-based rewards, the model doesn't get points for how it solves the problem, like did it use the tool correctly at step 5? No. It only gets rewarded for the final result. Did it get the right answer to the math problem? Yes or no. Simple binary feedback.
So the model just tries something, generates a whole sequence of text, maybe includes some code calls, maybe not, and then the system just checks the final answer at the very end.
Pretty much. If the final answer is right, big reward, high five. If it's wrong, zero reward, nothing.
Huh. So that structure, it really encourages exploration, doesn't it? The model is free to try solving it just with reasoning. Maybe try one tool call, maybe try multiple calls, maybe in a weird order.
Exactly. Through trial and error, guided by that simple correct and correct feedback and the RL optimization process, it gradually learns which sequences of actions, including generating the specific tokens needed to invoke a tool, ultimately lead to that positive outcome signal, getting the right answer.
And the specific goal of ZeroTIR, then, is to apply this outcome-based ZeroTIR framework directly to the problem of tool use.
That's the hypothesis. Take a base LLM, one that hasn't been specifically pre-trained on using tools. Train it using only these outcome rewards on tasks where tools could be helpful, like math. The idea is that it can spontaneously discover that using an external tool like that code interpreter is actually a highly effective strategy for maximizing its reward.
So it learns to use the tool autonomously because that behavior gets reinforced by success. It learns to want to use the tool because using the tool helps it achieve its goal.
It's a really powerful concept. It shifts from imitation to discovery based on achieving the desired outcome.
And just to quickly reiterate why code execution is the preferred tool here for math compared to maybe searching the web or something.
Yeah, it comes back to that need for precision and a deterministic process in math. Searching the web might find you relevant text snippets, formulas, maybe even similar problems, but that information can be noisy, incomplete, or it might still require the LLM itself to perform calculations based on it, which brings us right back to the original problem of the LLM's computational unreliability.
Right.
A code interpreter, though, especially for a language like Python with its rich libraries, it provides a perfect deterministic environment. You give it code, it executes it exactly according to the rules of the language, and it gives you back a predictable, verifiable output or maybe a clear error message if the code was bad. That rapid, unambiguous feedback loop is precisely what you need for the kind of exact computations and logical checks that mathematical problem-solving demands.
Okay, this is where it gets really interesting then. How did they actually do it? What are the nuts and bolts, the technical details of this ZeroTIR methodology? How do you train a model to spontaneously execute code using just outcome-based RL?
Yeah, this is the real technical heart of the paper, and they definitely had to tackle some significant challenges. The foundation is pretty standard in one sense. They use policy gradient RL algorithms. The paper mentions PPO and reinforce plus plus meg.
Okay, PPO and reinforce plus plus plus. Common RL algorithms.
Right, and the goal of these algorithms is to optimize the LLM's policy. The policy is just the model's way of deciding what token to generate next, given the history, right? It's a probability distribution over the vocabulary. The RL process adjusts the model's internal parameters, its weights, to increase the probability of generating sequences of tokens that ultimately lead to a high final reward, which in this case is getting the correct answer to the math problem.
So the model tries different sequences of words and code triggers, it gets feedback, incorrect, and the RL algorithm subtly nudges its internal thinking process to make it more likely to try the successful sequences again in the future.
That's the basic loop, yes. But integrating an external tool, like a code interpreter, throws a wrench into the works compared to standard text-only RL. The big issue is handling the tokens that are generated by the environment, not by the model itself.
Right. Because when the model outputs, say, the Python trigger, the system steps in, runs the code, and then injects the result, or maybe an error message, back into the conversation history that the model sees.
Yeah, exactly. And those environment outputs, those results from the code execution, they are tokens in the sequence, but the model didn't choose to generate them.
They're observations from the world, not actions taken by the agent.
Precisely. Yeah. In RL terms, that's exactly right. Standard RL algorithms, especially the ones like PPO that use value functions. Well, value functions are designed to estimate the expected future reward from a given state, a sequence of tokens. But critically, they estimate the value of states from which the agent can choose an action. States that consist purely of tokens generated by the environment are different. The agent didn't act to get to that specific state.
So the RL training process needs to be smart about this. It can't just treat those environment-generated states the same way it treats the states where the model is actually deciding what token to spit out next.
Exactly. It needs to properly handle these non-agent states. For example, when calculating the value loss, that's the part of the RL objective that trains the value function to be accurate, you shouldn't really train it on states that are just made up of environment output tokens. The paper mentions techniques like masking out these states during certain loss calculations.
Masking them out. So you just ignore them for that part of the calculation. Essentially, yes. You prevent the RL algorithm from getting confused by trying to assign value to or learn from parts of the sequence that the model itself didn't generate. This helps ensure the value function is primarily learning the value of the model's own decision points, the moments where it's choosing the next token.
Okay, that makes sense.
Okay.
And there's a related challenge you mentioned, reward attribution.
Yes, this is absolutely fundamental in RL. The policy updates the adjustments you make to the model's parameters based on the reward must only reinforce or penalize the actions taken by the model itself. The credit, or blame, for the final outcome needs to be correctly attributed back through the sequence of tokens that the model generated, leading up to the decision points where it might have generated code or decided to continue reasoning or whatever.
You can't, give the model credit for the number 2304 that the Python interpreter printed out. Exactly. The model didn't choose those specific tokens, 23004. It chose the tokens that formed the Python code request. So the framework needs careful bookkeeping to make sure the policy gradients, the updates to the model's weights, only apply to the model's own output tokens.
Okay, so managing that intricate dance between the model's generated tokens and the environment's injected tokens is a core technical hurdle they had to solve. Beyond that, you mentioned they use techniques for training stability and efficiency. RL training can be notoriously tricky.
It really can be. Interactive RL, especially with large models, can be unstable and slow. They highlight a couple of key techniques they used. First one is called replay buffer filtering.
Replay buffer filtering, okay.
So in RL, the model often learns from experiences past attempts at solving problems that are stored in a kind of memory, a replay buffer. Instead of just using all these past attempts equally for training, they filter them. They group the attempts or trajectories by the initial problem prompt. Then they check the accuracy of the final answer for each attempt.
And they filter based on that accuracy.
Yes. They specifically focus the training effort on attempts where the accuracy is in an intermediate range. They filter out attempts where the model was getting the answer right almost all the time, say greater than 80% accuracy for that prompt, and also filter out attempts where it was getting it wrong almost all the time, say less than 20% accuracy.
Wait, why would you filter out the highly successful attempts? Wouldn't you want the model to see more of those to learn from success?
It seems counterintuitive, doesn't it? But the thinking, which is pretty common in RL practice, is that the strongest learning signal, the steepest gradient for improvement, comes from situations where the model is kind of on the edge. Sometimes it gets it right, sometimes it gets it wrong.
Ah, okay.
If the model's already nailing a problem with 80% accuracy, there's arguably less marginal value in training on yet another successful attempt for that same problem. It kind of already knows how to do it. Conversely, if it's failing miserably, 20% accuracy, the trajectory might be so far off base that the feedback isn't very helpful for making small, useful adjustments. It might just be noise.
So you focus the training compute on the near misses and the partial successes in that middle range, where a small tweak might push it over the edge to correctness more reliably.
Exactly. That's where the RL algorithm can often make the most effective updates. It's like when you're studying for a test, you probably focus most on the problems you got partially right or just barely wrong,
Right.
right? Not the ones you aced easily or the ones where you had absolutely no clue how to even start.
Yeah, that makes a lot of sense, actually. Okay, so replay buffer filtering for stability and efficiency. What was the other technique?
The other one is about making the interaction mechanism itself more efficient. They use dynamic stop tokens and a kind of state machine approach. It's described in Figure 3 in the sources. The key idea is to avoid letting the model just generate a huge chunk of text and then trying to parse it afterwards to find code.
Instead, it monitors the output more actively, waiting for that specific code trigger, like Python.
Yes, exactly. The framework actively monitors the model's output token by token. As soon as the model generates that start of code trigger, like Python, the framework intercepts. It pauses the model's text generation right there.
Okay.
Then the framework extracts the code that follows, usually up to the closing code block marker. It sends that extracted code snippet off to the separate code execution environment service. It waits for the result to come back from that service. Then it formats that result, whether it's the output of the code or an error message, and injects that formatted string back into the context that the model sees.
And then it lets the model continue generating text.
Exactly. The model resumes generating from that new state, which now includes the outcome of its code execution attempt. It creates this very structured, interactive loop. Model generates, framework intercepts on tool call, framework runs tool, framework feeds result back, model continues.
That sounds much more robust and efficient than just hoping the model generates a complete well-formed response and then trying to parse everything out at the end.
It generally is. It allows for more fine-grained control. And this mechanism also makes it easy to enforce practical constraints during training and evaluation, like setting a maximum number of tool calls allowed per problem. They call this NMAX.
NMAX, okay. Why limit the number of calls?
Mostly for practical reasons, managing computational resources during training, preventing runaway loops if the model gets stuck calling the tool over and over. The framework can just count the calls, and if the model tries to make call number nmax plus 1, the framework can just intercept that, maybe inject a message like tool call limit reached, and let the model try to proceed without the tool from there.
Got it. Resource control. And you mentioned they built this whole environment interaction system to be pretty robust.
They did. They recognized that if the code execution environment crashes, maybe the model generates buggy code or the environment itself has an issue, you don't want that to bring down the entire potentially very long RL training run. So their initial setup used a decoupled service approach.
Decoupled, meaning the code interpreter runs as a completely separate process.
Yeah, like a separate microservice, maybe running in its own container, accessible over the network. The main RL training framework communicates with this external service to run the code. The big advantage is robustness. If the interpreter service handling one specific code snippet crashes, it doesn't kill the main training job. You just log the error, maybe give a negative reward, and move on.
That makes sense. Easier to manage, too.
Hmm.
They mentioned using standard web tech like Flask and Nginx for this.
Yep, things like Flask, Gunicorn, and Jinx, AO Limiter, basically standard tools for building scalable and resilient web services. It makes the whole system more maintainable.
Okay, so a reliable separate service for code execution. But you also mentioned they found ways to speed things up even more. That interaction could still be a bottleneck.
It could, yeah. Even with a separate service, if the main training loop has to synchronously wait for the network request to go out, the code to run, and the result to come back before it can proceed, That waiting time adds up, especially if you're running many training workers in parallel. It can become an I/O bottleneck.
So how did they improve on that?
They implemented asynchronous rollout and pipelining, specifically mentioning integration with an RL framework called OpenRLHF. The core idea is to break the dependency of waiting. Instead of one process doing everything sequentially, you have different processes working in parallel.
Like an assembly line.
Exactly like an assembly line. You have rollout actors. These are processes whose job is just to interact with the model and the environment. They generate experiences. Model tries a problem, maybe calls code, gets the output and reward, and they don't wait around. They just push these completed experiences into asynchronous queues.
Okay, so they just keep generating interaction data.
Right. And then separately, you have the main trainer process. Its job is to continuously pull batches of these experiences from the queues filled by the rollout actors and use that data to compute the gradients and update the model's parameters.
So the generating of experiences and the training on those experiences happen concurrently.
Precisely. This concurrency means the system isn't sitting idle as much. While the trainer is busy doing its calculations, the rollout actors are already busy generating the next batch of experiences, interacting with the model and the code execution service asynchronously. The sources quote some pretty significant speedups from this.
How much faster?
They mentioned getting around a 1.6x speedup compared to more basic asynchronous methods, and over a 4x speedup compared to the initial synchronous decoupled setup. That kind of speedup is absolutely crucial for making large-scale interactive RL training practical and affordable. You can run more experiments, train bigger models, or finish training much faster.
Wow, okay, that's a serious engineering improvement. So we've walked through the problem. LLMs and math are hard, the motivation, learning spontaneous tool use is cool, and the technical implementation. ZeroTIR using RL, handling the environment interactions smartly, using tricks for stability and efficiency. Now, the payoff. The results. What did the experiments actually show? Does the ZeroTIR thing work? And what about these agent RL scaling laws?
Right, this is where the rubber meets the road. Did the approach actually yield good results? They trained models based on the Quinn 2.5 architecture, specifically the 7B and 32B parameter versions, using their ZeroTIR method. They call the resulting train model ZTRL. And they tested it on some pretty challenging math benchmark data sets, like AIM and Math 500.
Okay, AIM and Math 500. Known tough math benchmarks. So the central question, does training a model this way to spontaneously use a code tool actually make it better at solving these math problems compared to models that can't use tools?
The results in Table 1 of the sources give a pretty resounding yes. ZTRL significantly outperforms ZeroTIR baselines that were trained without the tool integration capability.
How significant are we talking?
Well, for instance, the 7B parameter ZTRL model achieved an average accuracy of about 52.3% across the AIM and Math 500 benchmarks. Compare that to other Zero models mentioned in the table, like SimpleRL0 at 39.1% or Eurus2 Prime at 39.7%. These didn't have a tool integration. So that's like a 12-13 percentage point jump just from adding the spontaneously learned tool use.
Yeah.
Pretty strong evidence.
Yeah, that's a solid improvement. Okay, so it beats models without tools. How did ZTRL stack up against models that were specifically trained or prompted to use tools, like the SFT or prompted TIR methods we discussed earlier?
This is actually one of the most interesting findings, I think. ZTRL, which remember was trained from a general base model, Quinn 2.5 base, to learn tool use spontaneously. It actually outperformed a math-specialized model that used prompted TIR. They compared it to Quinn 2.5 Math Instruct.
The one designed for math and told when to use tools.
Exactly. Math Instruct scored around 41.6% average accuracy on these benchmarks. ZTRL, trained from the general base model with ZeroTIR, scored 52.3%.
Wow. So the autonomously learned strategy was better than the explicitly prompted strategy, even when the prompted model was specialized for math.
That's what the results suggest, yeah. It hints at maybe the outcome-based autonomous learning allows the model to discover more effective or perhaps more flexible tool use strategies than the ones we might teach it through explicit instruction or fixed prompts. Maybe it learns better when and how to apply the tool.
That's fascinating. They also compared their ZTRL results to another project doing similar work around the same time called TURL.
Right. TURL was another concurrent effort applying ZeroTIR with tool-integrated reasoning to math problems. The paper notes a key difference. TURL started its training from a base model that was already specialized for math, Quinn 2.5 math base. ZTRL, as we said, started from the general Quinn 2.5 base model.
So TURL had a head start in a sense, started from a more relevant base.
You could argue that, yes. But despite starting from that less specialized foundation, ZTRL actually achieved a slightly higher average score on the combined AMath 500 benchmarks, 52.3% for ZTRL versus 51.8% for Toro.
Huh. So the zero-tier method itself seems really effective and robust, maybe even able to compensate for starting with a general-purpose model.
It definitely indicates the strength of the ZeroTIR methodology itself. It seems to transfer well and work effectively, even when applied to a general base model, getting it to perform competitively with methods starting from specialized bases.
Okay, and what about the link between performance and how often the models actually decided to use the code interpreter? Was there a clear connection?
Oh, absolutely. The sources show a really strong correlation here. Their ZTRL model exhibited a very high code usage proportion in something like 89% of the problems it attempted on the benchmarks. It generated and executed code. The TRL model also had high usage, around 83%.
89% and 83%. So they were using the tool most of the time.
Right. And crucially, both of these models, which learned to use the tool frequently, significantly outperformed the baseline models that didn't use the tool, which obviously had 0% code usage. This empirically confirms that the learned propensity to leverage the tool is strongly linked to their success rate on these math problems. It wasn't just generating code for the sake of it. It was effective tool use that was leading to the correct answers.
Okay, so the takeaway is autonomous tool use via ZeroTIR works. It's effective, and it seems competitive with, or potentially even better than, explicit SFT or prompting methods. Now, let's really dig into these agent RL scaling laws they identified. They got these by analyzing how performance changed when they tweaked various hyperparameters, right?
Yeah.
Looking at tables 2 and 3, figure 4. What were the key patterns that emerged?
Yeah, this is where they tried to find predictable relationships between training parameters and outcomes. One of the most fundamental scaling laws they observed relates to what they call the interaction budget, which is that NMAX parameter we discussed.
Right. The maximum number of times the model is allowed to call the code interpreter for a single problem attempt during training or evaluation.
Exactly. And they varied this limit. What did they find?
What happened when they changed NMAX?
Table 2 shows a really clear monotonic relationship. As they increased the maximum allowed tool calls, NMAX, from 0, meaning no tool use allowed at all, up to 4 calls, or even up to 20 calls in some experiments, the accuracy achieved on the evaluation benchmarks consistently improved.
So more interaction potential equals better results.
Pretty much, yes. Just going from NMAX 0 to NMAX 4 could boost the average accuracy by quite a bit, like 15 percentage points on some of the benchmarks mentioned. This looks like a foundational scaling law for this type of agent, providing the potential for more computational effort. Specifically structured as interactions with the tool during both training and evaluation, scales positively with the agent's ability to solve these complex problems.
Does it keep scaling indefinitely? Like, is NMAX 100 better than NMAX 20?
The gains definitely showed diminishing returns. The biggest jump was often from 0 calls to just 1 or 2 calls. Going from, say, 4 calls to 20 calls might have yielded only a small additional improvement, or sometimes none at all. It suggests that while interaction potential is important, there might be an optimal level, maybe around 4 calls for these specific tasks and models, beyond which further interactions don't help much on average.
Okay, so interaction budget scales positively up to a point. What about the model's own inherent capacity, its size? Did bigger models learn this tool use better?
Yes, this finding aligns perfectly with the general trend we see across almost all LLM tasks. Performance scaled positively with model size. They compared the 1.5 billion, 7 billion, and 32 billion parameter versions of the Quinn 2.5 base model, trained under similar ZeroTIR conditions.
And the results?
The larger models consistently achieved higher accuracy on the math benchmarks. The 32B model outperformed the 7B, which in turn outperformed the 1.5B. This just reinforces that the well-known scaling benefits of larger models, more parameters, generally means more capability extend directly to this complex task of learning autonomous tool integration for reasoning. Bigger is better here too.
No surprise there, perhaps. What about the choice of the RL algorithm itself? They compared PPO and reinforced ++ way. Did that make a difference?
It did, but perhaps more in terms of efficiency than final performance, at least at the 7B scale they compared them at.
Right.
They found that while both PPO and reinforced ++ could eventually reach a similar final accuracy level on the benchmarks, reinforced plus got there much, much faster.
Faster convergence.
Significantly faster. The graphs suggest reinforced ++ achieved its near-optimal performance after only about 400 training steps, whereas PPO took over 700 steps to reach roughly the same point. So this isn't necessarily a scaling law about the peak capability achievable, but it's a really important practical finding about training efficiency. Reinforce Plus seems to be much better, or at least quicker, at leveraging the training data and feedback signals to reach high performance in this interactive setting.
Interesting. So algorithm choice matters for speed. Did the type of math problems they trained the model on influence how it learned to use the tool? They mentioned using different data sets like ORZ57K and DMath.
Yes, tables 2 and 3 show that the choice of training dataset definitely had an influence. ORZ57K was described as being more heterogeneous, maybe a wider mix of problem types. DeepMath was described as being more proof-focused.
And how did that affect the results?
Training on DeepMath seemed to lead to slightly higher peak performance, especially on metrics like max at K, which measures the accuracy if you generate K different responses and just check if any of them are correct. So maybe the proof-focused data helped it explore solutions that could hit higher peaks occasionally.
Okay, higher peaks with DeepMath. What about ORZ57K?
Training on the more heterogeneous ORZ57K dataset yielded better majority performance. That's the MAGI at K metric, which checks if the most common answer across K samples is correct. It also led to slightly better average performance across the board.
So ORZ57K led to more robust or consistent performance.
That seems to be the implication. It's fascinating insight, really. Even when the core task is learning this meta skill of using a tool, the specific nature of the problems and solutions the model sees during training subtly shapes the resulting capabilities. One dataset might push it towards hitting higher peaks occasionally, while another pushes it towards greater average reliability and consistency.
That makes sense. The training data always matters. What about the decoding strategy used during inference when you're actually asking the trained model to solve a problem? Things like temperature or top sampling.
Yeah, they looked at that too, specifically varying the top value, which controls the randomness or entropy in the decoding process, and they found the expected trade-off.
Trade-off between what?
Between peak accuracy and robustness or consistency. Using a higher entropy setting, like TOPI 1.0, which considers all possible next tokens, could sometimes allow the model to stumble upon a correct answer in one out of many tries, leading to a higher peak accuracy score, like max at 32.
But downside?
The downside was lower robustness. The agreement between different generated samples was lower, so metrics like majority voting accuracy, MAGE, and average accuracy, AVG, tended to suffer. Conversely, using lower entropy, like TOPI 0.7, which restricts the choices to a smaller set of more probable tokens, boosted the consistency and agreement across samples, improving MAGE and AVG metrics, usually with only a modest hit to the absolute peak potential.
So how you ask the model for the answer matters too. You can tune it for exploration and hitting high peaks, or tune it for consistency.
Exactly. It shows that the inference parameters interact significantly with the model's learned capabilities and how those capabilities actually manifest when you use the model.
Okay, now, there was that really counterintuitive finding you hinted at earlier, something about the training interaction limit, NMAX, during training, versus the evaluation performance.
Ah, yes. This one, highlighted in Table 3, is really thought-provoking. They ran experiments where they varied NMAX during training and then evaluated the resulting models also using different NMAX values. And they found cases where lowering the maximum allowed tool calls during training, say, training with NMAX 2 instead of NMAX 4, actually improved the model's accuracy when it was later evaluated with a higher interaction limit, like NMAX 4.
Hang on. Training with fewer opportunities to use the tool made it better at using the tool when given more opportunities later. That seems completely backwards.
It does, doesn't it? For example, on the AME25 benchmark with the big 32B model, the version trained with NMAX 4 achieved 50% max accuracy when evaluated at NMAX 4. But the version trained with only NMAX 2, when evaluated at NMAX 4, its accuracy jumped to 66%.
Wow. Why would that happen? What's the theory?
The researchers speculate a bit. It might be that for these larger, more capable models, they can actually learn effective core strategies for using the code tool relatively quickly. If you give them too much freedom early on, a very high NMAX during training, especially starting from a general base model, they might waste time exploring overly complex multi-step tool use strategies that are just harder to get right consistently. These might involve intricate error handling or passing intermediate results back and forth in ways that are fragile.
Okay.
By slightly restricting the interaction budget during training, like setting NMAX to 2, you might implicitly be encouraging the model to converge faster on more concise, higher utility single-call code strategies that are simply more robust and easier to learn reliably.
And those simpler, more robust strategies then transfer better when you give the model more freedom, a higher NMAX during evaluation.
That's the hypothesis. It learned a core, efficient way to use the tool under constraint, and that efficient strategy performs well even when the constraint is lifted. It's a fascinating potential insight into the learning dynamics. It suggests that simply providing more resources isn't always better. Sometimes subtly shaping the search space for strategies through constraints might lead to more robust learning.
That really complicates the simple more is better scaling idea.
It certainly adds nuance. These empirical findings, taken together, are what the researchers package as these agent RL scaling laws. They're trying to map out these observable, often quantifiable relationships between the resources you invest, model size, interaction budget during training, number of training steps, and the resulting capability of the AI agent to autonomously acquire and effectively utilize tools like the code interpreter.
Okay, so we've seen the patterns in the final performance based on different settings. Let's switch gears slightly and look at how this ability to use the tool actually emerged during the training process itself. Figures 1 and 4 in the sources track some metrics over training time. What do they show?
Yeah, looking at the training dynamics over time gives us some really key insights into the learning process. One of the most revealing graphs is the one showing the code proportion. That's basically tracking how often the model attempts to generate and execute code as training progresses.
And what does that curve look like? Does it start high?
No, interestingly, it doesn't. It often shows an initial dip, or maybe it stays low for a while before starting to rise significantly as training goes on.
An initial dip, like it tries not using the tool first,
That's right.
or it tries and fails.
It could be a combination. Initially, the base model might have very little inclination to generate the specific trigger sequence, like Python. Or, even if it does generate the trigger, the code it generates might be syntactically invalid or logically useless, leading to errors and no reward. So the RL process needs time to first train the model just to generate the right trigger tokens at the right time, and then, crucially, to generate code after that trigger that is actually useful and correct.
So the rise in the code proportion curve over time really represents the agent learning that invoking the tool is a valuable behavior. It's discovering its utility.
That's exactly the interpretation. It's empirical evidence of the spontaneous emergence of tool use as a learned strategy.
And how does that rise in just using code correlate with actually getting the problems right? Is it learning effective use or just learning to output code?
That's where another metric they track comes in. Code in, correct. This measures the proportion of problems where the model got the correct final answer and it used the code tool somewhere in its solution process.
Okay, so success with code.
Right. And this code incorrect metric is shown to rise sharply, pretty much in parallel with the overall raw reward average, which is just the average reward the model is getting across all attempts, indicating its general success rate on the task.
So the model getting better overall is happening at the same time as it's getting better at succeeding by using code.
Exactly. It's strong evidence that the agent isn't just learning to generate code randomly. It's specifically learning to use the tool in ways that directly contribute to successfully solving the problems and achieving that positive reward signal. It's learning effective, goal-directed tool use.
They also track response length, right? Does that tell us much?
It generally increases over training, which makes sense, right? Because responses that include code blocks and the output from the code execution naturally have more tokens than responses that are just pure reasoning.
Sure, more stuff in the output.
But, as the sources rightly note, while longer responses often correlate with tool use, response length by itself isn't a perfect indicator of correctness or even effective tool use. You could have a long response with useless code. The key insight comes from linking the code usage directly to the reward and correctness metrics.
Okay. Now, you mentioned earlier, and this came out of the scaling law analysis too, perhaps the most striking emergent pattern they found was about the frequency of tool use in the successful solutions. Even when they gave the models a generous budget of allowed calls NMAX up to 20 years, the models didn't learn to make lots of calls.
No, it's really quite surprising. They converged on using the tool very minimally. Across all attempts, successful or not, the average number of actual tool calls used per problem stabilizes at a very low number, typically somewhere between 1 and 2 calls, even when they were allowed many more.
Only 1 or 2 calls on average, even if they could have used 20.
That's right. But the really stark finding comes when you zoom in and look only at the attempts that resulted in a correct final answer and use the tool.
What did they find there?
The analysis shows that over 90% of the problems that were solved correctly using code execution relied on only a single code execution call.
90%, with just 1 call.
Over 90%, yeah. Fewer than 10% of the correct tool-using solutions involve two or more separate code execution calls.
That is genuinely surprising and a really powerful emergent strategy, isn't it? The model, basically left to its own devices under this simple outcome-based RL reward, doesn't learn to build complex, multi-step chains of tool use. It learns to use the tool minimally, but decisively. Get in, get the calculation done, get out.
It's a key finding, I think. It strongly suggests that for this type of mathematical reasoning task, the RL process heavily rewards strategies where the model identifies one crucial computation or check that can be reliably offloaded to the code interpreter, executes that one call correctly, and then perhaps uses that single result to complete the rest of the problem through its own reasoning.
And what are the implications of that? Why would it converge so strongly on this minimal single call strategy?
The researchers speculate, and it seems plausible, that it's likely related to the inherent difficulty and fragility of generating complex multi-step tool interactions correctly, especially during the early stages of learning. Trying to chain multiple code calls where the output of one call needs to be correctly parsed, interpreted, and maybe fed as input into the next code call that's just much more complex and prone to errors.
Errors in the model's reasoning about how to use the intermediate results, or errors in the code itself?
Both, potentially. Getting that whole chain right requires more sophisticated planning and execution from the LLM. Any error along the way in a multi-step process could derail the whole solution and lead to zero reward.
Whereas a single well-chosen code call is simpler, more robust.
Exactly. The RL signal would naturally tend to reinforce the simpler strategies that are more likely to succeed consistently and yield that positive reward. So the model effectively learns that figure out the single most important piece to compute externally, get that right in one go with the tool, is a much more reliable path to success than attempting elaborate, potentially fragile, multi-call procedures.
So the learning signal itself, by focusing purely on the final outcome, implicitly optimizes for the most reliable path to that outcome, which for this task and this tool seems to be a single high-impact tool use.
Precisely. It tells us something really important about the nature of the tool use that tends to emerge spontaneously under this specific outcome-based RL paradigm, at least for these kinds of mathematical problems, with a deterministic tool like a code interpreter.
This has been a really fascinating deep dive. Let's try and bring it all together and recap the main takeaways for everyone.
Sounds good. So to summarize, I think the core message from this research is that it provides clear empirical evidence that large language models, even starting from a general purpose base, can indeed learn to autonomously acquire and utilize external tools like a code interpreter for tasks that require precise computation, such as mathematics. And they can learn this simply by being trained with outcome-based reinforcement, learning the ZeroTIR approach.
And crucially, this learning process isn't just some magic black box. It seems to follow observable, somewhat predictable patterns, which the researchers termed agent RL scaling laws. We saw that performance scales positively with the computational resources invested during training, both in terms of the model size itself and the opportunity the model has to interact with the tool, that NMAX budget, although with diminishing returns.
Right. And then there was that surprising but really significant finding about the emergent strategy the models converged on. Even when given ample opportunity to make multiple tool calls, the successful strategies predominantly relied on just one highly effective code execution. The models learned to use the tool minimally but impactfully.
The significance of this work feels pretty substantial. It moves the conversation beyond just demonstrating that models can use tools if we explicitly tell them when and how, to showing that they can actually learn to make that decision spontaneously because they figure out it's the best strategy to achieve their goals.
Exactly. It gives us a more foundational understanding of how this kind of autonomous skill acquisition might happen in AI agents. And it also provides a solid, reproducible benchmark and methodology for future research, exploring these agent capabilities further.
Now, the researchers themselves, they pointed out limitations in future work, right?
Yes, absolutely. They frame this primarily as an empirical demonstration of these scaling laws and the feasibility of the approach. They note that more rigorous quantitative analysis is needed to understand the precise mathematical form of these scaling relationships, like, is it a power law or something else? That's future work. They also suggest exploring training without any hard constraints on the number of interactions, NMAX, to see what kinds of potentially more complex strategies might emerge if the model has complete freedom, even if it's harder to train.
Okay. And just thinking about that really striking emergent strategy, that strong preference for single effective tool calls, it makes you wonder, Given that the RL process here, focused on just getting the final answer right, seem to favor these reliable, simple, single-step tool uses. What does that imply for the kinds of tool use we can expect to emerge spontaneously from similar outcome-based RL when we apply it to much more complex tasks, tasks that might genuinely require intricate, multi-step interactions?
That's a great question. Or what if the tool itself wasn't as clean and deterministic as a code interpreter? What if the tool was, say, interacting with a physical robot, or querying a noisy database, or navigating a complex software interface? Would the learning patterns fundamentally change? Would the agent still converge on minimal interaction, or would the task demands force it to learn more complex chaining?
Yeah, it really makes you consider the difference between an AI agent being theoretically capable of performing a complex sequence of tool interactions versus the agent actually learning through RL that the simplest, most reliable interaction that achieves the goal is the optimal path, given that specific reward structure. Is that outcome-only reward signal maybe inherently pushing agents towards minimal risk, minimal interaction strategies whenever possible?
It's definitely something to ponder. It suggests the design of the reward function and the learning environment is going to be absolutely critical as we try to build agents that can tackle increasingly complex, multi-step problems in the real world.
A lot to think about as we continue to watch AI agents develop the ability to operate and solve problems more autonomously. This has been incredibly insightful. Thanks for guiding us through this deep dive into how AI models are learning to spontaneously reach for the right tool for the job.
It was a pleasure. Really interesting work.
Absolutely. We'll catch you, the listener, on the next deep dive.